Right, hello everyone. Here we are on the second session of stage 2, and today, for this session, we have Frank Lemmer, who's a director of Sowento, and he's talking about a physics-based sensor tracking digital twin for enhanced reliability of floating wind farm monitoring solutions. Very interesting because, of course, there's not really that many floating wind farms around, but the number is going to grow dramatically over the next 5 to 10 years. So it'll be interesting to see how we can optimize those. So, Frank, I'll pass over to you.
Great.
And just for everybody else's advantage, please remember to use Q&A to ask any questions. Feel free to type them in as they occur to you as we go through it, and then we can ask them at the end. Thanks, Frank.
Great. Thanks a lot, John, for the introduction. It's an immense pleasure to be here at this very well organized conference and present OSIA, our physics-based sensor tracking digital twin, which we are developing at Sowento in collaboration with AMOG. Let me start right away. Hope you can see the next slide. So before I go into any technical details, let me introduce our two companies. First of all, AMOG, more than 30 years of experience in the offshore industry, industry leaders in mooring integrity management, which is one of the core topics I'm going to address today, and product owners of the Smart Marine Integrity Checker SMIC, which has been in operation for many years. It's proven by regulatory societies. So this is a very, very established product in the oil and gas industry. We are building up on this product. You can see a screenshot there. But now over to Sowento. Sowento has been established quite some years ago, two divisions, floating wind simulation controls, the one I'm leading. The other one is wind LiDAR, LiDAR-assisted control, so turbine control. That means Sowento has a lot of experience in wind turbines, how wind turbines work, how wind turbine controllers work, and how they influence the dynamic behavior, especially of floating offshore wind turbines. Sowento owns and operates the in-house SLOW simulation software. That's an integrated loads analysis software comparable to OrcaFlex or OpenFast. And that software has one particular advantage, which is it works in real time, so orders of magnitude faster than other simulation tools. And of course, that will go into the digital twin of OSIA. I will talk more about this software and about the physics behind it and how we make it possible to run simulations that fast. Just a second to, yeah, now I have the right screen. So again, let me introduce a few terms, a few general terms. We have heard a few talks about digital twins today, but what do we mean by digital twin? What is a digital twin? So first, why do we need it? Of course, the offshore environment is a harsh environment. Mooring integrity management is constrained by limitations in accessibility. Then it's very cost sensitive, so it's very hard to scale traditional oil and gas monitoring methods. So we need new, more efficient methods and methods that are adapted to floating offshore wind. And the Core Wind, that's an EU project which is recently completed. As the deliverable has shown that digital twins are really a technology which has the highest potential to provide an economic monitoring solution. Now, what is a digital twin? Of course, there's a real asset, and then the idea is that the digital twin is a digital replicate of the real system. But there are a few particular features and advantages which we think are important for digital twins. So first, it's not one signal that we're looking at, like one load that we're measuring. It's really a multitude of sensors, often differing for different projects. So I'm going to talk about that in a bit later as well. So it's multiple sensors. We need to combine all this data set, this source of information with a global digital twin, which covers many physical disciplines. So it's a multi-physics model. And then a model-based filtering is something that I'm going to talk about as well. Sensors always include noise. There's always only a limited precision of all the sensors that are on the market. So we always need to make sure that we get the sense of all the sensors while removing all the unphysical noise. So there's different ways of filtering that noise. I'm going to talk about the model-based filtering approach in a bit. And then the third advantage that we see in digital twins is the virtual sensing. Physical sensors, they are always placed in discrete locations. So one example is that we can get continuous deformation for most of the sensors along, for example, pontoons of a semi-submersible, along the tower and along the blades. So that virtual sensing is a way, as soon as we have the digital twin aligned and tuned with the physical asset, we can get all this continuous data to augment the discrete physical information. What are we monitoring? So what are we talking about today? I'm talking about loads. I'm talking about excursions, displacements. So it's people talk a lot about structural health monitoring. That's what we mean a lot. I going to talk about fatigue here, especially about the mooring lines. And there's a distinct challenge in tracking fatigue. So that's much harder than tracking extreme events, extreme responses, because we need a very, very high accuracy in fatigue tracking. So what is state-of-the-art methods? We have on the left-hand side, we have purely data-driven models. On the right-hand side, we have physics-based models. What we have seen in the literature, there is no purely data-driven models at this point, which are just fed by sensor data. It's most of the time, it's simulation models, which are simulation response data fed into an AI system, and that then is tuned then to the simulation responses. So that's like this hybrid model in between. But the problem with that is that you require a huge database of simulation results. So you need to run very, very extensive training data in order to tune the digital twin. So what is our motivation before I now go into the details of our approach? So first, we want to really leverage the data that we are measuring. There's very good sensors, very good and accurate sensors. Of course, everybody wants to do that. But then on the other hand, we see there's so much experience in feed. So detailed engineering. There is a very well-tuned ILA model available in projects. So we want to leverage all that information. And we have this physics-based model, this slow software, which aligns very well with OrcaFlex. So we're going to use that. But then in addition to that, we want a very lean and modular solution. So we want to avoid these training data sets. So what I'm going to present today is a physics-based model, which does not require any training. It shall be very easy to adapt it. Why do we need to adapt a digital twin? So here are some examples on the sensitivity of the response and especially fatigue loads with a focus on moorings from the EU Sudoku project, a recent deliverable. We can see that small changes, which are not unrealistic, have a huge effect on the fatigue life. So what are the reasons for such changes? The as-built model is never exactly the as-designed model. So once we have a physical system, we always see deviations. Once we have a demonstrator in place, we obtain measurements, and then we can calibrate against those measurements. And later, throughout the life, we can do calibrations against inspections. So what are the reasons for changes in the system? It's of course adverse events like the synthetic mooring stiffness change. We all know that there's creep depending on extreme events, degradation as well. Marine growth is a big effect which influences the mass per length of a mooring system, the mooring diameter via marine growth as well. So we have these system changes, and we definitely, as we see on the slide, need to adapt the digital twin to such changes. People also call this different digital twin levels, like level 1 to level 5. So the more calibration and validation exercise you conduct, the higher the level of the digital twin. But now, after I've introduced all the background and motivation, let me introduce the core concept of OSIA. So the core of the monitoring and the digital twin of OSIA is a Kalman filter. Many of you might have heard about Kalman filters from the literature. Is not a very new approach. It's quite established. It's being used in robotics and many other industries. And there are academic papers on this approach applied to wind turbines and floating wind turbines by NREL and also by Sowento. So to our knowledge, we are the only ones to apply this approach to an industrial product. So what happens in a Kalman filter? One thing is we have model predictions. So there's a digital twin, which gives us predictions. And then we have measurements, different sensors across the entire system that can be the turbine, that can be strain gauges, can be motion, like GPS measurements, IMU measurements, acceleration, inclination, etc. These two are fed into the Kalman filter, which then comes up with an optimal prediction based on that information. And how is this done? The Kalman filter calculates the optimal prediction based on the known uncertainty of the model. So we know how uncertain the model is and the different predictions of the different states because we built up the physical model. We have all the knowledge about it. And the same with the measurements. Once we have the specs of the sensors, we know the uncertainty of the sensors, and then we are constantly measuring the noise in the sensors. So the Kalman filter can, at every instant of time, optimize the prediction. So how, let me say a few words about the digital twin. I mentioned the slow software. It is a software which we use also in design tasks, but here the core is really the same that we use in the digital twin. It's an aero-hydro-servo-elastic model, so it has the turbine aerodynamics, it has the controller inside, it has structural dynamics, hydrodynamics, mooring dynamics, of course, and we even have an elastic hull model, which is the subject of the ongoing IEA OC7 project. So this year the focus is on elastic hull effects. This is also included. I mentioned the computational speed. So a 1 hour simulation completes in 5 seconds up to 120 seconds. And that we can do that via a hybrid symbolic numeric programming approach. So this makes it possible to run even a nonlinear model in real time here for the system. But now let me say a few more words on how agile this approach is, because we wanted to to adapt the system for all the different components from the turbine down to the cable in a simple way. So let me talk about what happens once we feed sensor data into the system. The first thing is we have a module which ensures the quality of the measurement data. So we detect sensor failures. We also detect the noise levels. As I explained before, that's inherent in the Kalman filter algorithm. And then we have an online system identification module. Of course, that does not happen in every instance of time. So this is like a slow adaptation to the system properties. But this goes into the OSIA digital twin system. So the first thing is we update the system parameters of the model. And the nice thing here, because it's fully physics based, as soon as we make a change in the input files of the model, we immediately see the response and the change response to that in the results. The updating of the state observer, like the Kalman gain, that happens automatically in the Kalman filter algorithm based on the sensor information and the current measurements of the sensor. How does this integrate into the overall structure of OSIA? I've already explained the central part of this slide. On the right-hand side, you can see the standard features of our software and dashboard. Of course, a secure interface, etc. But the important thing on the scientific part is the continuous system identification, the sensor quality assessment, which happens also in real time. And based on that, we can then do a failure detection, because once we're sure about the system properties, which change throughout the lifetime, and the quality level of the sensors, we can do a very accurate and low uncertainty failure detection. Let me talk a little bit about the sensors that we use. On the left-hand side, you see all the sensors that are possible. We have a lot of wind LiDAR experience, but of course, not every turbine has a LiDAR. So we usually say the more sensors we have, the smaller the uncertainty. So the better for the prediction. But it really depends on the project which sensors we have. So our approach is very modular. But it is important to say that in most cases we have more sensors than we need. So it's kind of a least squares optimization. You could think of it. So we want to get the best prediction based on the sensors that we have. Let me proceed to a mooring fatigue case study, which we did for this presentation. Why moorings? Of course, they are hard to inspect, same as the cable, and it's very hard to monitor mooring fatigue. I will talk about that in a bit. But first of all, the base scenario we're looking at, it's the IA 15 megawatt Volturnus semi-submersible. It's not the standard all-chain mooring system. It's what we use here is a hybrid semi-taut mooring system, which was recently published by NREL in an ocean engineering paper. The sensors of this study are the turbine operational data, like the Scala data, rotor speed, blade pitch angle, generator torque, tower strain gauges, and then load cell, GPS and IMU, which is sensors on which we often get questions from project developers, like which accuracy is needed. So we focus on that. And then the goal of this study is to look at virtual load cells. That means that the model and the Kalman filter predicts the green ones, which is the virtual sensors. And for this study, we have used OpenFast results, and we added noise to these OpenFast simulation results based on the specs from the sensor suppliers. And then we show how the Kalman filter is able to really take the sensor data and the model prediction in every instance of time and merge that together into an optimal prediction. You will see that in an animation on the next slide. So we see here the upwind and the downwind fairly tension. We see the OSIA prediction, that's the Kalman filter prediction, so the optimal prediction in blue. And we see the ideal, so the exact mooring tension, which is obtained from OpenFast simulations in orange. So that orange, that's not the measurement. That's really the ideal and exact load. We could have shown the noisy sensor data as well, but that would have made it more difficult to really see the alignment. But we can see that really in every instance of time, we can track the sensor data. So that really means that it's a phase resolved digital twin. We can really track the behavior in every instance of time. So this is not on a statistical level like other digital twins. Let me show you a power spectral density in the frequency domain as well. So here in the spectrum is the same signals, but now we can see the peaks, the frequency peaks, like system resonances, also first order wave spectrum. Maybe you can see my mouse here at around 0.1 hertz, and then we can see the tower natural frequency at 0.5 hertz, and just below 0.4 we see the blade passing frequency. So all those are in here, and as I promised at the beginning, I was talking about filtering. So just applying a low pass filter, filtering out the noise at higher frequency would clearly mean that we get rid of the noise, but at the same time, we also get rid of system resonances. And that makes especially the mooring fatigue prediction very inaccurate. So that's not what we want to do. And that's an approach which is not scalable, because by placing the cutoff frequency, you kind of tune the response, and then it's not physics based anymore. So this is what we call a model based filtering, which the Kalman filter is able to do. So we can see here, we can cover all of the peaks by the digital twin. So that's exactly what we need. And finally, we can see the damage of all the three lines, upwind and downwind. Upwind is the most experiences the most loading, so that's the most important one. And we can see that the damage, so this is really the total damage, which gives you the lifetime, is below 5% for that line and below 10% for the other line. So that's a very good result compared to what we have seen in literature and what we had in earlier versions. That's very, very promising. Before I end, let me say a few words about farm-wide implementation. I talk about different levels of instrumentation, but our approach is to recommend a high level of instrumentation here for the red ones and less instrumentation for the yellow ones. And how do we do that? You can see here results of the Carbon Trust commercial scale mooring integrity management project, where we see that depending on the position of a turbine and the criticality of that turbine, we want to reduce the uncertainty of the prediction as much as possible for that turbine. And of course, the more sensors we have, the lower the uncertainty. And then we can learn from that and update digital twins for the other ones as well. So we reduce the uncertainty for the other turbines as well. The cost, just quickly, we calculated some scenario here with 11 turbines with high instrumentation, 39 turbines with less instrumentation, and we end up with only a third of the cost of the fully instrumented floating offshore wind farm. Right, that brings me to the end of my presentation.
Okay.
So let me recap what was the goal. We wanted to have a very flexible and modular approach, combining multiple sensors with a physics-based model, and able to be changed and modified throughout the system lifetime. So we have made this possible. The extended Kalman filter works for the mooring fatigue prediction. And just a few words on how we what we do next. We are currently spending a lot of time and delivering results to the TetraSpar project, where we apply OSIA to. We are starting another project very soon, which I can't disclose yet. So stay tuned, and thank you very much for attending. And I'm looking forward to answering any questions.
Okay, great. Thanks, Frank. Unfortunately, we are a few minutes over on the pure presentation side, so we've kind of run out of time for questions. There's no questions in the chat though, anyway. So I'm going to assume there's nothing burning. Otherwise, I'll have stopped you and we'd have covered those. So thanks for it. Really interesting talk about that. Very fascinating future technology as we get into more into floating offshore wind. So thank you for your time today. I will close the session and we'll get on to the next one.
Thank you.
Great. Thanks, Frank.